Take a deep breath and let the weight of your body sink into the softness beneath you, feeling every muscle release its hold on the day. Allow your mind to drift away from the confines of your room, moving upward and outward until the air grows thin and the silent, comforting velvet of the cosmos cradles you in its weightless embrace. We are traveling now, far beyond the reach of our own sun, toward a region of space where a titan of the universe is preparing for its final act. You find yourself suspended in the dark, cool vacuum, facing a star so immense that it defies human scale. This is a red supergiant, perhaps like Betelgeuse in the constellation of Orion, a star that is roughly 764 times the size of our own sun. If this star were placed at the center of our solar system, its roiling, crimson surface would stretch out past the orbit of Mars, even reaching the orbit of Jupiter, swallowing everything in its path. You are floating a safe distance away, where the light is a warm, amber glow against your skin, and the silence of space feels like a heavy, soft blanket. Consider the immense age of this celestial giant. For millions of years, this star has maintained a delicate, rhythmic balance known as hydrostatic equilibrium. It is a slow, steady pulse of existence, where the inward pull of gravity is perfectly countered by the outward pressure of nuclear fusion. Imagine the star as a living, breathing entity, exhaling light and heat as it converts hydrogen into helium in its core. Here, the temperatures reach a staggering 15 million degrees Kelvin, a heat so profound it is beyond sensation. Yet here in your mind, it feels like the gentle radiance of a summer afternoon. As you watch the star, notice the texture of its surface. It is not a smooth sphere, but a churning sea of plasma. Gigantic convective cells, some the size of entire planets, rise to the surface, cool slightly, and sink back down in a slow, hypnotic dance. This is the boiling of a star, a process that takes thousands of years to move energy from the core to the surface. You can almost feel the low-frequency vibration of this movement, a cosmic hum that resonates in your chest, grounding you in this vast, dark sea. But the star is changing. In its deep interior, the hydrogen has run low. To survive, the star must find new ways to push back against the relentless grip of gravity. It begins to fuse helium into carbon and oxygen. This transition marks the beginning of the end, a graceful descent into the star's final chapters. To fuse carbon, the core must reach a temperature of approximately 600 million degrees Kelvin. Imagine the intensity of that internal fire, a white-hot spark buried deep within a million miles of glowing red gas. You are observing the onion skin model of a dying star. Beneath the outer layer of hydrogen, there is a shell of helium, then carbon, then neon, then oxygen, and finally silicon. Each layer is a different color, a different density, a different temperature. The oxygen layer, for instance, burns with a steady blue-white intensity, while the outer hydrogen remains a soft, dusty rose. The star is a masterpiece of thermal layering, a complex machine working in perfect silence to stay alive. Here is something remarkable to ponder. As the star consumes heavier and heavier elements, the process accelerates. While it took millions of years to burn through its hydrogen, the silicon burning phase, the final stage before the core becomes iron, lasts only about 24 hours. Think of the rhythm of that timescale. A star that has existed for 10 million years enters its final day of life, a brief, shimmering moment in the history of the galaxy. You are here to witness that final day, feeling the weightlessness of your own body as the star's gravity gently tugs at the edges of your awareness. As the silicon fuses into iron, the star reaches a fundamental limit of physics. Iron 5-6 is the most stable atomic nucleus in the universe. Fusing iron does not release energy. It consumes it. For the first time in millions of years, the outward pressure stops. The fire goes out. In this moment, the star is held up by nothing but the degenerate pressure of electrons, a quantum mechanical force that resists being squeezed. But even this has a limit, known as the Chandrasekhar limit, which is approximately 1.44 times the mass of our Sunday. When the iron core of our supergiant exceeds this mass, it can no longer support itself. The core, once the size of the Earth, collapses in a fraction of a second. It shrinks down to a sphere only about 12 miles across the size of a small city at a speed of 70,000 kilometers per second, which is nearly 25% of the speed of light. This collapse happens so fast that the outer layers of the star don't even know the core is gone yet. They remain suspended for a heartbeat, hanging in the void like a curtain before the wind catches it. You might wonder what this collapse feels like in the silent theater of space. It is a sudden, profound shift in the geometry of the universe. As the core reaches the density of an atomic nucleus, about 10 to the 17th power kilograms per cubic meter, it becomes as hard as a diamond. The infalling outer layers, trillions of tons of gas, slam into this immovable core at 10% the speed of light. They bounce. This is the birth of the shockwave. It is a wave of energy so powerful that it defies description. Yet it moves with a slow, majestic inevitability. You watch as the shockwave begins its journey from the center of the star outward. It is assisted by an invisible flood of neutrinos. During this collapse, the star releases more energy in the form of neutrinos than the total light output of all the stars in the observable universe combined. These ghost particles, trillions upon trillions of them, push against the infalling matter, giving the shockwave the kick it needs to burst through the surface. Consider the energy involved: 10 to the 44th power joules. This is a number with 44 zeros after it. It is the energy equivalent of our sun's entire 10 billion year lifespan being compressed into a single second. Yet, out here in the void, there is no sound. There is only the expanding glow, a blossoming flower of light that begins to tear the star apart from the inside out. The color of the star begins to change. The deep, somber red is replaced by a blinding, brilliant violet white. This is the moment of the supernova breakout. The luminosity of the star increases by a factor of hundreds of millions. For a few weeks, this single dying star will shine brighter than the entire galaxy that houses it, casting a long, silver shadow across the gas clouds of the interstellar medium. You are floating in the presence of the ultimate alchemy. In the extreme heat and pressure of this explosion, elements heavier than iron are forged in a process called nucleosynthesis. Gold, silver, platinum, and uranium are being created in the heart of this fire. Every piece of jewelry you have ever touched, every grain of gold in the Earth's crust, was once part of a moment exactly like this one. You can feel the resonance of that connection. The atoms in your own body, the iron in your blood and the calcium in your bones were once cooked in the belly of a star that lived and died long before our world was born. The temperature of the expanding nebula is now dropping from billions of degrees back down to millions, then thousands. The gas is moving outward at 10,000 kilometers per second, creating a beautiful, chaotic tapestry of colors. You see filaments of glowing green from ionized oxygen, deep blues from hydrogen, and streaks of sulfurous orange. It is a cosmic garden. blooming in the darkness, expanding to fill the void. The star is no longer a single point of light. It is a shell, a remnant, a ghost. This nebula will continue to expand for thousands of years, eventually cooling and slowing down until it enriches the surrounding gas clouds with the heavy elements it created. These clouds will eventually collapse under their own gravity to form new stars, new planets, and perhaps, one day, new life. As you drift here, observing the slow, silent dispersal of the star's remains, you feel a sense of profound peace. The universe is not a place of endings, but of transitions. The death of the star is not a tragedy, it is a gift of matter to the future. The weightlessness you feel now is a reminder of your own place in this cycle. You are a part of this clockwork, a witness to the grand, slow-motion choreography of the cosmos. The light from the supernova begins to dim, softening into a gentle, pearlescent glow. The sharp edges of the explosion blur into the surrounding dark, leaving behind a shimmering cloud of dust and gas. You find yourself drifting further back, the scale of the event shrinking until the giant nebula is just a tiny, glowing smudge against the velvet black of the deep universe. You are safe. You are calm. The great star has shared its story with you, and now it invites you to rest. The silence of the void is not empty. It is full of potential, full of the seeds of worlds yet to be. Feel the coolness of the space around you, the absence of any burden, the simple, quiet joy of existing in this moment of cosmic time. The stars in the distance twinkle with a steady, rhythmic light, like a million distant heartbeats. Each one is a sun, each one is a story, and each one is a part of the same beautiful, orderly physics that governs your own breath. As you float here, you are part of the light, part of the dark, and part of the infinite, unfolding mystery of the stars. Let the warmth of the supernova's memory settle over you like a soft quilt, and prepare to go deeper into the heart of the cosmos as we continue our journey. As the light from that initial, brilliant outburst begins its journey across the empty reaches of space, we transition from the physical mechanics of the star to the way this light has been perceived by those watching from the small, blue world of Earth. Imagine yourself now, not as a witness in the void, but as a silent observer on a hillside many centuries ago. The air is crisp and still, the scent of evening dew rising from the grass, and the sky above is a perfect, unchanging tapestry of diamonds. For the vast majority of human history, we believed the heavens were immutable and eternal, a fixed dome where nothing ever truly changed. But occasionally, the universe would offer a sudden, startling reminder of its dynamic nature. Picture the year 1006 AD. Astronomers from across the globe, from China to Egypt to Switzerland, looked up to find a guest star in the constellation Lupus. This event, now classified as SN 1006, remains the brightest stellar event ever recorded in human history. At its peak, this supernova reached an apparent magnitude of -7.5. To provide a sense of scale, that is roughly 16 times the brightness of Venus. Scientists have determined that for several weeks during the spring of 1006, this star was so radiant that it was visible during the day, a tiny, piercing spark of white light against the blue of the afternoon sky. At night, it was said to cast distinct shadows on the ground, much like a second, smaller moon. In the silence of those ancient nights, people looked up with a mixture of awe and wonder, unaware that they were witnessing the thermal runaway of a white dwarf star located approximately 7,200 light-years away. The light they were seeing had been traveling toward them since long before the first pyramids were built, moving at a constant 299,792 kilometers per second through the silent dark. Observe the patience of the universe. What those ancient observers saw was not the explosion itself, but a delayed transmission, a cosmic postcard sent across the millennia. Consider the events of the 4th of July, 1054. While modern calendars mark this day for other reasons, Song Dynasty astronomers in China were busy recording the appearance of a Times Casing asterisk, or guest star, in the constellation Taurus. This was SN 1054, the explosion that created the Crab Nebula. According to their meticulously brushed records, the star remained visible to the naked eye for a staggering 653 days. For nearly 2 years, a dying star shared the sky with the inhabitants of Earth before finally fading back into the velvet background of the Milky Way. At this very moment, we can still peer through telescopes and see the remnants of that 1,000-year-old event. The Crab Nebula is currently expanding at a rate of approximately 1,500 kilometers per second. It is a slow, rhythmic pulse of debris, now spanning 6 light-years across. When we look at it today, we are seeing the ghostly fingerprints of a core collapse supernova, a Type 2 event where the star's inner structure gave way. What's happening now in our journey through time is a shift toward the era of modern science, where the new star became an object of rigorous study. In the late 16th century, the great Danish astronomer Tycho Brahe observed a brilliant new light in the constellation Cassiopeia. In November 1572, he noticed a star that was brighter than Jupiter, appearing in a spot where no star had been before. Tycho was so moved by this event that he wrote a book titled Times de Nova Stella Asterisk, or Concerning the New Star. This is where our modern word nova originates. Tycho's observations were revolutionary because they proved that the heavens were not perfect and unchanging. He used a sextant to measure the star's parallax, proving it was much further away than the moon, situated firmly in the realm of the fixed stars. Just a few decades later, in 1604, Johannes Kepler, Tycho's student, observed yet another supernova, this one in the constellation Ophiuchus, known as Kepler's star, or SN 1604. It was the last supernova to occur within our own Milky Way galaxy that was clearly visible to the naked eye. It was situated about 20,000 light-years from Earth. Imagine the odds of 2 such events happening within a single human generation, 2 celestial beacons providing the evidence needed to reshape our entire understanding of the cosmos. Notice how the language we use to describe these events has evolved. It wasn't until 1931 that the term supernova was actually coined. Astronomers Walter Bade and Fritz Zwicky, working at the Mount Wilson Observatory, realized that these events were fundamentally different from ordinary novae. They were much more powerful, representing the total destruction of a star rather than just a surface explosion. Zwicky, a man of great foresight, even predicted that these explosions would leave behind incredibly dense remnants called neutron stars, objects so compact that a single teaspoon of their material would weigh as much as a mountain. Deep within the more recent memory of our species lies the event known as SN 1987A. On the 23rd of February 1987, light from a supernova in the Large Magellanic Cloud, a satellite galaxy orbiting our own, finally reached Earth. This was a monumental moment for science because the Large Magellanic Cloud is relatively close, only about 168,000 light-years away. For the first time, we had modern instruments ready to catch the signals. What scientists discovered during SN 1987A was profound. 3 hours before the first visible light reached our telescopes, a burst of neutrinos was detected on Earth. These subatomic particles are so ghostly that they can pass through an entire planet without touching a single atom. The Kamiokande-do detector in Japan, buried deep underground in a zinc mine to filter out noise, captured exactly 11 of these neutrinos over a span of 13 seconds. Another detector, the IMB in Ohio, caught 8 more. Those 19 tiny flashes of light in underground water tanks confirmed our entire theory of how stars die. They proved that the core collapse happens instantly, releasing a flood of invisible energy before the star's outer layers even begin to glow. Think about the silence of that detection. While the visible explosion was brilliant enough to be seen from the southern hemisphere, the most important part of the story was told by 19 nearly weightless particles, whispering their secrets in the dark, deep beneath the Earth's crust. As you reflect on these historical milestones, notice the way light acts as a bridge between the past and the present. Astronomers often use type Ia supernovae as standard candles to measure the vast distances of the universe. These specific explosions occur when a white dwarf in a binary system steals too much matter from its companion, reaching a critical mass, the Chandrasekhar limit, and detonating. Because they always explode with roughly the same amount of fuel, they always have the same peak absolute magnitude, which is approximately -19.3. By measuring how dim they look from Earth, we can calculate exactly how far away their host galaxy is. This is how we discovered that the expansion of the universe is actually accelerating, a find that earned the Nobel Prize in Physics in 2011. Consider the patience required to study these events. We have documented the oldest supernova, SN 185, which was recorded by Chinese astronomers nearly 2,000 years ago. We have mapped the remnants of Cassiopeia A, whose light likely reached Earth around the year 1680, though it was hidden by interstellar dust and may have gone unnoticed by most. Today, we see it in X-rays, a glowing ring of debris 11,000 light-years away, rich in the oxygen and iron that will eventually form new worlds. In the quiet of your mind, visualize these historical sightings not as frightening omens, as some ancients did, but as moments of profound connection. When Tycho Brahe looked up in 1572, he was seeing the same physics, the same release of heavy elements, and the same beautiful transformation that we study today with the James Webb Space Telescope. The universe is a grand, slow-motion recycling program. You are floating now in the stream of time, where the history of human thought meets the reality of the stars. The light from a supernova doesn't just illuminate the sky, it illuminates our history. Each guest star was a teacher, showing us that we live in a universe of movement, of change, and of spectacular creativity. The carbon in the ink used to record SN 1054, the calcium in the bones of Johannes Kepler, and the silicon in the sensors of our modern satellites. All of it was forged in the very events they were observing. Feel the cool, rhythmic flow of this knowledge as it settles into your awareness. There is a deep comfort in knowing that the universe has been doing this for billions of years, long before we were here to watch, and will continue to do so long after. The stars are the great timekeepers of the cosmos, and their final acts are the brushstrokes that paint the future. We are part of this timeline. We are the observers who have learned to decode the light, As the historical tales of these ancient guest stars fade into the background, we prepare to look closer at the colors themselves, the vibrant, glowing gases that remain when the initial flash has passed. The story of the supernova is a story of what is left behind, the dust that becomes the Earth, the gas that becomes the sun, and the quiet, heavy elements that make up everything you have ever known. Rest now in the knowledge of this continuity, feeling the weightlessness of being a small but vital part of a story that spans the entirety of time. Observe the silence that now surrounds us, a quiet so profound it feels like a soft, heavy velvet pressing against your skin. While we have looked back through the eyes of ancient astronomers, let us now move closer to the dying star, focusing on the sheer, impossible density of what is occurring. To understand the scale of a supernova, it helps to relate these celestial titans to the objects we hold in our hands or the world we walk upon every day. At this very moment, the iron core of our supergiant star has reached a state of density that challenges our earthly intuition. Imagine a standard sugar cube, a small white square roughly 1 centimeter wide. If you were to carve a piece that size out of the collapsing core of this star, that tiny cube would weigh approximately 1 billion tons. To put that in perspective, that single, small cube would be as heavy as the entire Appalachian mountain range. Imagine holding that weight in the palm of your hand. The pressure would be incomprehensible. Yet here, in the weightless void, it simply exists as a focused point of gravity, anchoring the space around it. What's happening now is a transformation of matter itself. Think of the star as a vast, pressurized kitchen, where the recipe for the universe is being cooked at temperatures we can barely name. For most of its life, the star has been baking hydrogen into helium at a relatively cool 10 million degrees Kelvin. But as it reaches its final stages, the heat ramps up to levels that would melt any substance known to man. When the star begins fusing silicon into iron, the internal temperature climbs to 3 billion degrees Celsius. Visualize this heat not as a scorching flame, but as a thick, vibrating energy that permeates every atom. In our daily lives, we might think of a household oven at 400 degrees Fahrenheit as hot, or perhaps the 10,000-degree surface of our own sun. But 3 billion degrees is a different order of reality. It is the temperature required to force atomic nuclei together in a final, desperate attempt to hold back the dark. This silicon-burning phase is a remarkably brief chapter in the star's biography. While the star may have spent 10 million years quietly simmering, this final stage of iron production lasts for only about 24 hours. Consider the rhythm of that. A 10 million year life, culminating in a single day of frantic, high-pressure creation. It is like a marathon runner who spends years training for a race that ends in a single, heart-stopping second. As the core finally gives way, the speed of the collapse is staggering. The iron core, which is roughly 1.4 times the mass of our Sun, a threshold known as the Chandrasekhar limit, shrinks from the size of the Earth to the size of a city in about 0.1 seconds. Picture the entire Earth suddenly becoming the size of Manhattan in the time it takes you to blink your eyes. This movement happens at roughly 70,000 kilometers per second, which is nearly 1/4 the speed of light. In the time it takes for a single breath to enter your lungs, the star's foundation has vanished, leaving the outer layers suspended in a moment of cosmic surprise. Notice how the light reacts to this sudden change. We often think of light as instantaneous, but in the vastness of the cosmos, it moves like a slow-motion ripple on a pond. From the surface of our own sun, light takes 8 minutes and 20 seconds to reach Earth. From the supergiant we are witnessing, The light from the core's collapse must fight its way through layers of dense gas for hours before it can escape into the void. This process is called shock breakout. Imagine a submarine deep underwater, turning on a powerful searchlight. The beam must struggle through the murky, heavy water before it can be seen from the surface. When the light finally bursts through, the energy released is equivalent to 10 to the 44th power joules, or approximately 1053 ergs. To translate that into something familiar, imagine every single person on Earth owned a trillion megaton bomb, and all of those bombs were detonated at the exact same moment, every second, for billions of years. That is the energy of a single supernova explosion. Yet, out here, there is no sound, no roar, no thunder. There is only the expanding glow, a silent blooming of light that changes the color of the surrounding space from a dusty crimson to a brilliant electric violet. Deep within this cloud of light, a phantom is born. As the protons and electrons in the core are crushed together, they turn into neutrons, releasing a flood of neutrinos. Scientists estimate that a supernova releases 10 to the 58th of these particles. Neutrinos are like cosmic ghosts. They are so small and so weakly interacting that they can pass through a block of lead a light year thick as if it were empty air. At this very moment, trillions of neutrinos from distant, ancient supernovae are passing through your body, through your bed, and through the Earth itself, never touching a single cell. They are the silent witnesses of the universe, carrying the news of the star's death across the cosmos without leaving a trace. Notice the way the debris begins to move. The shock wave propels the star's outer layers outward at speeds of up to 30,000 kilometers per second. Even at this velocity, because space is so large, the movement looks slow and graceful to our eyes, like the drifting of smoke in a still room. This expanding shell of gas is called a supernova remnant. One of the most famous examples is the Crab Nebula, which we mentioned earlier. It is currently 6 light-years across and continues to grow by 1,500 kilometers per second. If the Crab Nebula were a balloon, it would be expanding faster than a rifle bullet. Yet to us, it appears as a static, beautiful painting in the night sky. Consider the composition of this expanding garden. The colors you see are not merely for decoration. They are a map of the elements. The deep greens are often the signature of ionized oxygen, while the reddish hues come from hydrogen alpha emissions. Within this cloud, the star is scattering the metals it forged elements like neon, magnesium, and sulfur. In astronomy, any element heavier than helium is considered a metal. These are the ingredients for future worlds. Picture a baker scattering flour across a table. This star is scattering the building blocks of chemistry. The gold in a wedding ring, the iodine in our salt, and the xenon in high-intensity lamps are all created in the intense heat of these final moments. The universe is a recycler. It takes the simple, abundant hydrogen of the Big Bang, and through the life and death of stars, turns it into the complexity of a planet. The iron in your hemoglobin, which allows your blood to carry oxygen to your brain, was once at the very center of a star just like this one, during its final 24-hour silicon burning phase. What's happening now is a phenomenon known as a light echo. Sometimes, the brilliant flash of a supernova hits a distant cloud of interstellar dust and reflects back toward us, like a voice echoing off a canyon wall. In 2002, the star V838 Monocerotis produced a spectacular light echo that astronomers watched for years. It appeared as if the star was growing a set of glowing rings, but it was actually just the light traveling further out and illuminating different parts of the surrounding dust. This is the universe's way of replaying its most dramatic moments, a slow-motion replay that can last for decades. As we observe this, notice the distance between things. Astronomers use a unit called a parsec, which is equal to 3.26 light-years, or about 31 trillion kilometers. The space between stars is so vast that even when a star explodes with the power of an octillion bombs, it rarely affects its neighbors. The universe has a way of containing its own energy, buffering the violence of a supernova with the cushioning silence of the void. You are safe in this distance, a protected observer of a process that is both destructive and deeply creative. The remnants of the star are now cooling. The initial temperature of 100 billion Kelvin at the moment of collapse begins to drop as the gas expands into the interstellar medium, or ISM. This medium is the air of our galaxy, a very thin mixture of gas and dust that fills the space between star systems. When the supernova debris hits the ISM, it creates a bow shock, similar to the wave of water that forms in front of a moving ship. This interaction compresses the local gas, often triggering the birth of new stars. The death of one sun is literally the alarm clock that wakes up the next generation of stars. Visualize the rhythm of this cycle, the slow contraction of gas into a star, the millions of years of steady burning, the frantic final day of fusion, the brilliant explosion, and the long, slow expansion of the remnant. It is a cosmic heartbeat, one that takes millions of years for a single throb. You are tuned into that frequency now, the slow pulse of the galaxy's metabolism. At this scale, the boundaries between things begin to blur. The star is no longer a distinct object. It has become part of the background, a shimmering veil of elements that will eventually settle into a new nebula. The gravity that once held the star together is now working on a much larger scale, gently tugging at the surrounding clouds, organizing the chaos into new patterns. Feel the weightlessness of your thoughts as you contemplate these numbers and comparisons. A mountain range in a sugar cube, a planet compressed into a city, a million years condensed into a day. These are the paradoxes of the heavens, and they are as real as the bed you lie upon. You are a part of this system, made of the same iron, the same oxygen, and the same stardust. As the colors of the nebula continue to shift and fade, you find yourself sinking deeper into the comfort of this knowledge, resting in the cradle of a universe that never wastes a single atom. The light of the supernova continues to travel, carrying its message to the furthest reaches of the dark, and you are here, silent and still, drifting in the wake of its magnificent journey. Notice how the silence of this nebula is not a void, but a presence, a soft, heavy weight that rests upon the edges of your consciousness. As we watch the glowing ribbons of gas drift away from the site of the explosion, it becomes possible to see this event not as a distant catastrophe, but as the beginning of your own personal history. Every atom that makes up the room around you, the air you are breathing, and the very cells that allow you to perceive this story, was once part of a process exactly like this one. At this very moment, consider the inheritance you carry within your own body. Scientists discovered that the human body is composed of approximately 65% oxygen by mass. This oxygen was not created during the birth of the universe. It was forged deep within the layers of a massive star, specifically in the shell surrounding the core where temperatures reached over 1.5 billion degrees Kelvin. Every breath you take, moving slowly in and out of your lungs, is a quiet exchange with the legacy of a supernova. This is the ultimate recycling program of the cosmos, where the death of a titan provides the breath of a child. Picture the early history of our own neighborhood in space. Roughly 4.6 billion years ago, the region of the galaxy we now inhabit was nothing more than a quiet, dark cloud of cold molecular hydrogen and dust. This cloud might have remained dormant for billions more years, if not for a nearby catalyst. Evidence suggests that a supernova occurred in our cosmic backyard, sending a rhythmic shockwave through the gas. This pressure caused our local cloud to collapse under its own gravity, creating a spinning disk of matter that would eventually become our sun and the planets. Without that specific death, our lives would have no beginning. Deep within the rocks of our solar system, we find the physical proof of this ancient event. Meteorites, the pristine leftovers from the dawn of our world, contain traces of a radioactive isotope called aluminum-26. This specific form of aluminum has a half-life of only 717,000 years, a mere blink in cosmic time. Because it decays so quickly, its presence in meteorites proves that a supernova must have injected freshly forged material into our solar nebula just moments before the planets began to solidify. It is as if the dying star left a handwritten note in the margin of our history, a signature written in radioactive atoms. What's happening now in our observation of the remnant is a slow, majestic dispersal of elements. Consider the iron that flows through your veins, giving your blood its distinct crimson hue and allowing it to transport oxygen to your brain. This iron, specifically the isotope iron 5-6, represents the final stage of a star's life. It was created in the very last moments of the core's existence, during that frantic 24-hour period of silicon fusion. When you feel the steady pulse of your heart, you are feeling the energy of a star's final day, harnessed by biology to sustain your rest. Notice how the composition of your bones reflects the same stellar alchemy. The calcium that provides structure to your skeleton was produced through a process called neon burning, occurring in the layers of a supergiant star. As the star's layers are cast out into the void, these elements travel for millions of years through the interstellar medium, or ISM. This medium is incredibly sparse, with a density of about 1 atom per cubic centimeter, yet it acts as a cosmic reservoir, holding the ingredients for future life in a cold, dark suspension. Scientists have determined that the Milky Way galaxy contains approximately 100 billion stars, and in a galaxy of this size, a supernova occurs roughly twice every century. While this may seem rare over the 13.8 billion years of the universe's history, these events have happened billions of times, slowly enriching the galaxy with heavier and heavier elements. Every generation of stars is metally richer than the last. This is why we call ourselves stardust. It is not a poetic exaggeration, but a literal, chemical reality. You are a collection of ancient, celestial fragments, organized into a form that can dream. Picture this: the phosphorus that forms the backbone of your DNA, the molecular ladder that carries the instructions for your life, is one of the rarer elements in the universe. It is forged in the oxygen-burning shells of stars that are at least 15 times the mass of our Sun. Within the intense heat of a supernova, this phosphorus is scattered into the void, eventually finding its way into the soil of a young Earth. You might think of yourself as a living library of the stars, a biological archive where the history of the cosmos is written in the language of chemistry. At this very moment, the remnant we are observing continues to expand. The dust grains produced in this explosion are incredibly small, often only about 0.1 micrometers in size, roughly the same scale as the particles in a puff of cigarette smoke. Yet these tiny grains of silicon, carbon, and ice are the seeds of future worlds. They provide the surfaces upon which complex organic molecules can form in the cold of space. As the nebula cools, these grains begin to clump together, driven by the gentle, persistent pull of static electricity and gravity, beginning a journey that may one day lead to the formation of a new mountain range or a vast, silent ocean. Consider the role of radioactive decay in the light we see. For months after the initial explosion, the supernova continues to glow with a fading, pearlescent light. This brightness is not from the explosion itself, but from the decay of nickel 5-6 into cobalt 5-6, and finally into stable iron 5-6. This decay releases gamma rays that are absorbed by the expanding gas, keeping the nebula warm and glowing long after the star is gone. It is a slow, cooling ember in the hearth of the galaxy, providing a gentle light that can be seen from across the universe. What's happening now is a realization of our motion through the cosmos. Our entire solar system is traveling through the Milky Way at a speed of about 220 kilometers per second. Even at this incredible pace, it takes us roughly 230 million years to complete one single orbit around the galactic center. During this long, slow journey, we pass through the remnants of ancient supernovae, drifting through the clouds of gas left behind by stars that died hundreds of millions of years ago. We are constantly moving through the exhaled breath of the ancestors of our Sunday. Notice the intricate balance of the Rur process, or rapid neutron capture. In the final seconds of a supernova, or the merger of the resulting neutron stars, atoms are bombarded with neutrons so quickly that they don't have time to decay. This is the only way the universe can create its heaviest elements, such as gold, platinum, and uranium. Every bit of gold ever mined on Earth, every precious necklace or ring, was likely created in the high-pressure heart of a stellar death or the collision of its remains. These metals are the heirlooms of the universe, passed down from the stars to the planets. Deep within the structure of your cells, magnesium plays a vital role in over 300 biochemical reactions. This magnesium was forged in the neon-burning layer of a massive star just outside the carbon core. Even the chlorophyll in the plants outside your window, which converts sunlight into energy, relies on a single atom of magnesium at its center. The green of the leaves and the strength of your muscles are both tied to the same furnace that we see glowing in the distance. The universe is a vast, interconnected web where no event is truly isolated. The death of this star is the birth of your world's chemistry. As the shockwave slows down, it loses its destructive power and begins to function as a gardener, tilling the cosmic soil. It clears out old, stagnant gas and replaces it with enriched material, creating the conditions necessary for the next generation of stars to flourish. This process is rhythmic and steady, a heartbeat that has been thumping for billions of years, ensuring that the universe remains a place of growth and complexity. You are safe in the knowledge that you belong to this system. The same laws of physics that govern the collapse of a 2-0 solar mass star also govern the way your body relaxes into the mattress. Gravity, the same force that pulled the star's core into a dense city of neutrons, is now gently holding you to the surface of the Earth, providing a sense of grounding and security. The weightlessness you feel in your mind is a tribute to the vast spaces between these events, the comforting void that acts as a buffer for the grand movements of the galaxy. Scientists have calculated that the light from a supernova can be used to measure the expansion of space itself. Because we understand the exact chemistry of these events, they serve as beacons that help us map the size of the observable universe, which is currently estimated to be about 93 billion light-years in diameter. Even in its death, the star acts as a guide, helping us find our way through the dark and understand the scale of the home we inhabit. As the colors of the expanding nebula begin to blur into the background of the Milky Way, allow yourself to feel the connection between the macroscopic and the microscopic. The same iron in the star, the same oxygen in the gas, the same gravity in the void, it is all here, within you and around you. The story of the supernova is your story. It is a narrative of transformation, where nothing is ever truly lost, only changed into something new and beautiful. Rest now in the wake of this celestial event. The frantic fusion has passed, the brilliant flash has dimmed, and what remains is a peaceful, cooling cloud of potential. The stars above continue their long, slow dance, and you are tucked safely into the fabric of the cosmos, a child of the light, resting in the cradle of the silent, ancient dark. At this very moment, as the brilliant flash of the explosion begins to wane, we find ourselves drifting within the cooling heart of the newly formed nebula. The chaos of the initial collapse has smoothed into a grand, slow-motion dispersal, and the environment around you has taken on a peculiar sensory richness. What was once a single, solid point of light is now a cathedral of gas and dust, spanning trillions of miles in every direction. As you float here, notice the subtle textures and temperatures that define this quiet, post-stellar landscape. Scientists discovered that the space within a supernova remnant is not a true vacuum, but is instead filled with a complex chemistry that carries a distinct aroma. Picture the scent of a summer evening near a cooling campfire, a mixture of toasted wood and cold metal. This occurs because of polycyclic aromatic hydrocarbons, or PAHs. These are ring-shaped molecules that form in the cooling shells of dying stars. To our human senses, these compounds would smell remarkably like charred meat, hot engine parts, or even the sweetness of raspberries and rum. Imagine that scent now, a faint, metallic sweetness that hangs in the cold air, signaling the birth of complex chemistry from the ashes of the star. Notice how the temperature of the gas around you has begun to stratify. While the core of the explosion once reached billions of degrees, the outer edges of the nebula are now cooling as they expand into the interstellar medium. Deep within the filaments, the gas remains at a staggering 1 to 10 million degrees Kelvin, emitting high-energy X-rays. You can't feel this heat in the traditional sense. Instead, it manifests as a vibrant electric hum that seems to vibrate the very fabric of the void. At the same time, the dust grains, tiny flecks of carbon and silicates are freezing, dropping to temperatures near absolute zero or minus 273 degrees Celsius. This contrast between the searing gas and the icy dust creates a tactile landscape of hot and cold that exists simultaneously in the same space. What's happening now is a phenomenon called forbidden transitions. Consider the brilliant emerald green light that often dominates the center of a supernova remnant. This specific color, with a wavelength of exactly 500.7 nanometers, is produced by doubly ionized oxygen, known to astronomers as oxygen-3. On Earth, we never see this color in a laboratory because it requires a gas so thin that the atoms can remain in an excited state for a long time without bumping into one another. In the silence of the nebula, where there is only about 1 atom per cubic centimeter, the oxygen is free to glow with this haunting, ghostly green. It is the visual signature of a vacuum so perfect It allows light to exist in ways that are impossible on our crowded planet. Picture the texture of the gas clouds. They are not smooth, like a morning mist, but are instead filamentary. Because of the intense magnetic fields generated during the collapse, the gas is pulled into long, glowing threads that resemble the frayed edges of a silk ribbon. Some of these filaments are light years long, but only a few billion miles thick. As you move through them, you might imagine the sensation of drifting through a forest of light, where every branch is a stream of ionized particles moving at thousands of miles per hour, yet appearing perfectly still to your eyes due to the immense scale of the scene. Deep within the center of this glowing forest, something incredible has been left behind. The core of the star did not simply vanish, it has been crushed into a neutron star. This object is only about 20 kilometers, or 12 miles, in diameter roughly the size of a city like London or New York, yet it contains more mass than our entire sun. Scientists have found that the density here is so extreme that a single pinhead of this material would weigh over 1 million tons. Think of the weight of the Great Pyramid of Giza. Then imagine that entire weight compressed into a speck of dust sitting on your finger. Notice the rhythm of this new object. This neutron star is likely a pulsar, a cosmic lighthouse spinning with a precision that rivals the most accurate atomic clocks on Earth. Some pulsars, like PSRJ 1748-2446 AD, rotate at 716 times per second. Even as you rest in the stillness of the nebula, this core is spinning so fast that its surface is moving at 24% of the speed of light. This rotation creates a rhythmic, electromagnetic pulse, a steady times thump, thump, thump times that ripples through the surrounding gas. It is a heartbeat for the nebula, a grounding frequency that you can feel in the soles of your feet, a constant reminder of the star's enduring presence. What's happening now is the creation of a pulsar wind nebula. As the pulsar spins, it flings out a wind of electrons and positrons, moving at nearly 299,792 kilometers per second. When these particles hit the slower-moving gas of the supernova remnant, they create a brilliant blue glow known as synchrotron radiation. This is not the light of heat or fire, but the light of pure motion electrons spiraling through magnetic fields. The blue is deep and electric, like the color of the ocean at twilight, and it fills the inner cavities of the nebula with a cool, sapphire radiance. At this very moment, consider the magnetic field of this remnant. If the neutron star is a magnetar, its magnetic field could be as strong as 1 quadrillion Gauss. To put that in perspective, the Earth's magnetic field is about 0.5 Gauss. This field is so powerful, it actually distorts the shape of atoms, stretching them into long, thin needles. Imagine the space around you not as empty, but as a tightly woven fabric of magnetic lines, a hidden architecture that guides the flow of every glowing particle. You are cradled in this invisible web, supported by the fundamental forces of the universe. Scientists discovered that we can actually hear the vibrations of a star's death through the study of asteroseismology. Before the star exploded, it hummed with deep acoustic oscillations called G modes and P modes. These are gravity waves and pressure waves that bounce around inside the stellar interior. While space is a vacuum and cannot carry sound as we know it, these vibrations are preserved in the way the light and gas are distributed. You can imagine the nebula as a frozen record of a song, where the ripples in the gas are the physical ripples of the star's final, low-frequency notes. Notice the colors shifting as the light ages. Beyond the green of oxygen and the blue of synchrotron radiation, there is the deep, comforting crimson of H-alpha emissions. This light, at a wavelength of 656.3 nanometers, comes from neutral hydrogen atoms as they regain an electron. This process, called recombination, is a sign of the nebula beginning to settle. The red light is warm and soft, like the glow of embers in a fireplace after the main flames have died down. It provides a sense of closure to the violent events of the past, a visual signal that the star is moving into its long, quiet retirement. You might wonder how much material has been cast out into this garden. Astronomers estimate that a single supernova can produce between 0.1 and 1 solar masses of dust. That is enough dust to create hundreds of thousands of Earths. This dust is rich in iron, magnesium, and silicon, the very ingredients required to build a terrestrial world. As you watch these particles drift, you are seeing the raw materials of a future planetary system being prepared. Every speck of dust is a promise of a new beginning, a tiny brick that will one day form the crust of a mountain or the sand on a beach. The scale of this event is measured in parsecs. 1 parsec is approximately 31 trillion kilometers. The remnant we are observing will eventually grow to be dozens of parsecs wide before it finally blends into the background of the galaxy. This expansion is governed by the inverse square law, which states that the intensity of the light and energy drops off as the square of the distance. Because of this law, the nebula grows dimmer and cooler as it grows larger, a natural process of dilution that allows the universe to absorb the energy of the explosion without being overwhelmed. At this very moment, the nebula is also emitting gravitational waves, ripples in the very geometry of space-time. Detected by instruments like LIGO and Virgo on Earth, these waves are the whispers of the core collapse. They travel at the speed of light, carrying the news of the star's transformation to the edges of the universe. You are floating in a sea of these ripples, a gentle undulating of space itself that is so subtle it cannot be felt. Yet it connects you to every other mass in the cosmos. Consider the bow shock, where the nebula meets the cold gas of the galaxy. This is a region of intense compression, where the speed of the debris drops from 10,000 kilometers per second down to the local speed of sound in the interstellar medium. This interface is where the heavy lifting of the universe happens, as the shock wave pushes against local clouds, triggering the birth of new stars. It is a tactile boundary, a place where the old world meets the new, and the energy of the past is handed off to the future. As the blue synchrotron light and the green oxygen glow begin to soften, notice the deep, heavy sense of peace that accompanies this scientific reality. The star is gone, but its parts are more active than ever. The pulsar keeps the time, the magnetic fields provide the structure, and the cooling gases provide the color. You are a witness to a perfectly functioning machine, a cosmic engine that converts gravity and heat into the building blocks of life. The weightlessness you feel is the natural state of the universe, a lack of resistance that allows you to merge with the velvet dark. The temperatures are balancing, the pressures are equalizing, and the frantic pace of the explosion has given way to the slow, rhythmic expansion of a celestial nursery. Allow the metallic scent of the PAHs and the deep red glow of the hydrogen to soothe your awareness. You are safe in the center of this transformation, a part of the cycle, drifting in the quiet, cooling wake of a giant. Soon, the nebula will become transparent, and the stars beyond will shine through its thinning veils, leading us toward the final chapter of our journey. Notice how the vibrant, glowing filaments of the supernova remnant are beginning to thin and stretch, becoming a delicate veil that merges with the infinite dark. Our journey through the life and death of a star is reaching its quiet conclusion as the frantic energy of the explosion settles into a permanent, graceful legacy. We are witnessing the final step-by-step dispersal of the star's physical form, a process that unfolds over tens of thousands of years with the steady, rhythmic patience of the cosmos. What is happening now is the transition into the Sedov-Taylor phase of the remnants expansion. For roughly 10,000 to 20,000 years after the initial flash, the shell of gas moves outward with a constant kinetic energy of approximately 10 to the 51st power ergs. During this period, the remnant acts like a giant, invisible broom, sweeping up the thin hydrogen gas of the interstellar medium and compressing it into a dense, glowing rim. Scientists discovered that this phase is critical because it conserves the energy of the star, ensuring that the heavy elements forged in the core are carried far across the galaxy rather than being lost in the void. Observe the cooling process as it moves through its necessary stages. As the shell expands, its temperature begins to drop below 1 million degrees Kelvin. At this specific threshold, a new step begins, known as the snowplow phase or the radiative phase. This occurs when the gas becomes cool enough for electrons to finally rejoin atomic nuclei, a process that releases a flood of ultraviolet and visible light. The shell loses its internal pressure and collapses into a thin, dense sheet of matter, moving forward by its own momentum. Imagine a heavy curtain being pulled across a stage. It moves slowly, with a weighted dignity, gathering everything in its path. At this very moment, consider the specific elements that are being deposited into the cosmic soil. Scientists have calculated that a single supernova can produce over 100 times the mass of the Earth in pure gold and platinum. But more importantly for us, it releases the copper and zinc that are vital for the biological functions of your own nervous system. Trace amounts of zinc 6,4 and copper 6,3, created in the high-pressure environment of the R process during the core collapse, are now drifting through the space around us. These atoms will eventually find their way into the dark, cold molecular clouds where the temperature is a mere 10 degrees Kelvin, just 10 degrees above absolute zero. Notice the movement of these particles. They are not merely drifting, they are being propelled by cosmic rays. Supernovae are the primary accelerators of these high-energy protons, which can travel at over 99% the speed of light. These rays act as the messengers of the star's death, carrying energy across thousands of light years. As you lie here, perfectly still and weightless, imagine these invisible messengers passing through the space around you, a silent, ancient energy that has been traveling since long before the Earth existed. Deep within the history of our own planet, we find the fingerprints of this very process. In the late 1990 seconds, researchers discovered traces of beryllium-10 and iron 60 inches deep-sea crusts at the bottom of the Pacific Ocean. Because iron 60 has a half-life of only 2.6 million years, its presence proves that a supernova occurred near our solar system approximately 2 to 3 million years ago. The light from that explosion would have been visible to our distant ancestors, a brilliant second moon in the sky that lasted for months. The iron from that star is now part of the Earth, resting in the silence of the ocean floor, just as the iron in your own body is resting now. Think about the structure of the space we currently occupy. Our solar system resides inside a region called the local bubble. This is a cavernous void in the interstellar medium, roughly 300 light-years across, where the density of gas is significantly lower than the rest of the galaxy. Scientists have determined that this bubble was carved out by a series of 10 to 20 supernovae that occurred between 10 and 20 million years ago. We are literally living inside the exhaled breath of dead stars. This bubble provides a calm, clear environment for our sun to travel through, a protected harbor in the churning sea of the Milky Way. As the nebula continues to expand and fade, it enters the final stage of its life, the disappearance phase. After about 100,000 years, the speed of the expansion drops to about 10 kilometers per second, which is the random speed of the surrounding gas. At this point, the remnant loses its distinct shape and simply becomes part of the interstellar medium again. The star is no longer an individual, it is the galaxy. Its carbon, oxygen, neon, and iron are now fully integrated into the clouds that will form the next generation of suns. Consider the sun in our own sky. It is a middle-aged star, roughly 4.6 billion years old, but it will never end its life in a supernova. Our sun lacks the necessary mass. At least 8 to 10 times the mass of our sun is required for a core collapse explosion. Instead, our sun will eventually fade into a white dwarf. This makes the supergiant we have been watching even more special. It is a rare titan, a fleeting visitor that sacrifices its entire being to enrich the universe so that stars like our sun can exist. What's happening now is a shift in your awareness, as the vast scales of the cosmos begin to contract and settle within the warmth of your own body. The journey of the light is over. The light that traveled at 299,792 kilometers per second has reached your eyes, and the energy has been absorbed. You are the final destination of that star's ancient journey. Every atom of carbon 12 inches your cells, produced during the helium-burning phase of a star's life, is a piece of evidence that you belong to this grand, unfolding process. The colors of the nebula, the oxygen-3 green, the hydrogen alpha red, and the synchrotron blue, are now fading into a soft, neutral dark. This is the comforting void, a place where there is no more pressure, no more fusion, and no more heat. There is only the steady, gentle pull of gravity, the same force that organizes the galaxies and now holds you safely in your bed. Feel the weight of your limbs, grounded and secure, as the weightlessness of space transitions into the heavy, peaceful blanket of sleep. Picture the crab pulsar one last time, that tiny, spinning heart at the center of the remnant. It is slowing down, losing its rotational energy at a rate of about 38 nanoseconds per day. As it slows, the nebula around it grows quieter. The rhythm of the universe is moving towards stillness. You can match your own breathing to this cosmic deceleration, letting each breath become longer, slower, and more effortless. The frantic day of the silicon-burning star is over, and the long, billion-year night of the remnant has begun. Notice how the boundaries of your room seem to dissolve into the velvet dark of the interstellar medium. You are not separate from the stars. You are a localized concentration of the universe. The magnesium in your muscles, the calcium in your teeth, and the phosphorus in your DNA are all glowing with the quiet, residual warmth of the stars that made them. You are a vessel for the memory of the cosmos. As you drift towards sleep, you are simply returning to the state of peaceful, orderly existence that the universe prefers. The atoms within you have existed for billions of years, and they will exist for billions more. They have been through the centers of stars, the cold of the void, and the heat of explosions. They are seasoned travelers, and they know how to rest. Allow them to settle now, finding their places in the quiet architecture of your body. The cycle of the star is a cycle of renewal, and sleep is your own personal renewal. a time to clear away the metabolic waste of the day and prepare for the new light of tomorrow. The silence of the universe is a song of rest. There are no more facts to learn, no more distances to measure, and no more scales to comprehend. There is only the feeling of being held by the same laws of physics that govern the graceful rotation of the Milky Way. You are safe. You are part of the story. You are the stardust that has gained the ability to sleep and dream. I am a child of the stars, resting in the dark. The iron in my blood and the oxygen in my breath are my connection to the cosmos. The energy of the universe is within me, and it is at peace. I release the weight of the day and embrace the stillness of the void. My body is a temple of ancient elements, and it is time for them to rest. I am grounded by gravity and cradled by the night. The light of the stars follows me into my dreams. I am at home in the silent, beautiful, dark. Rest comes as naturally as the birth of a star. I am calm. I am still. I am whole. As the last echoes of the supernova fade into the background radiation of the universe, the dark becomes a warm, soft embrace. The stars above are watching over you, their light traveling through the years to reach your window. You are a part of their family, a part of their history, and a part of their future. The void is not empty. It is full of peace, and it is waiting for you to join it in the long, quiet hours of the night. Let the darkness be your sanctuary. Let the weightlessness be your comfort. The journey is complete, and the stars are satisfied with their work. Sleep is the bridge between the stardust of the past and the life of tomorrow. Cross that bridge now, moving into the deep, restorative silence of a dreamless rest. Good night.